attendance now in Moodle. We have 15 minutes as usual to do it. So the attendance is actually under the 11th September, okay, under week 1. So after you have punked the attendance, I mentioned that I want to talk about where you can get a recording, and it seems that our first recording, there are some problems with MS Teams. However, you can still download the recording. So you can get a recording actually at our Teams week 1 page. And if you scroll up here, you should be able to see this, this download button here. Okay, this download link here. Usually what happens is that after each recording, the recording will be provided a link whereby you can view the recording online. So typically I will make the recording a tab here. Okay, but however, in this case, it seems that there's something wrong with this MS Teams, I think more or less recently. So what we're going to do is that we're going to try again for today. Let's see if the recording goes back to normal. If not, then I probably have to contact SIT on this, okay? Because I'm not sure if it is a problem with MS Teams or SIT, okay? But I researched online and it seems that MS Teams has these recording problems recently, okay? So we're going to just stick with what we have been doing, and you can download this link, right, in case you need it and in case the so-called link does not get get corrected back. Okay, so by the way, this download link is actually expiring in 18 days. Okay, so if you want, you can download that. It's about 300 plus megabytes. So with that, we are going to continue today's lesson, or start on today's lesson proper. So for those who just joined, please mark your attendance. You have another 30 minutes to do so. So just a recap on what we have gone through. Basically, we have gone through the concept of functions, right? What constitute a function? Basically, a function takes an input. Can be multiple inputs, but in this course, we'll be looking at single variable functions or single valued functions, where you take a single input, for example, x, and then go through an operation, right? Operation on the input, and then it produces an output y, okay? For example, denoted by y. And we looked at the domain and range of the function. Basically, the domain refers to the input values x, and the range refers to the output values of y, that the function can be defined properly. So those are the domain and ranges. And then subsequently, we also looked at symmetry, some of the transformation or symmetry properties of a function. And then we are at the stage whereby we looked at even and odd functions. So even function is a function that is reflected, that when you view the function, it appears as a reflection over the y-axis. Okay, so the left half or the right half of the function is actually symmetrical to the left half, okay, and vice versa, of course. So for an odd function, the symmetry presents itself as a rotation of 180 degrees about the origin. So therefore, if you look at this expression here, it seems that this first quadrant curve can be rotated to the third quadrant over the origin and over 180 degrees. So if you have something like that, then we say that this satisfies the odd definition. So to check whether a function is odd or even, one way is that you can plot the graph and analyze. Another more concrete way is to look at the conditions mathematically. So we mentioned that the condition, right, for an odd function is actually the function value at negative x must be equivalent to the negative of the function value at its positive x. So you can see this is f of x, and you can see this is f of minus x, and they are exactly negative of each other. So therefore, this is the condition for an odd function to be defined. So this is the mathematical condition that you can check. So similarly with the even function, there's also a mathematical condition, and that is actually f of minus x is equals to f of x. Okay, now take note that not all functions will satisfy the symmetry property of being even or odd. Okay, and there can be also functions that are neither even or odd. Okay, in fact, most functions, right, they are neither even or odd here. So let's look at this example to make this more concrete. So first of all, if you look at part A, right, whereby you have f equals to x to the power of 5 plus x to the power of 5 plus x. Now, as I mentioned, the way to check this using mathematical equations, right, is to substitute the minus x into the x. Okay, so just let x be minus x and then evaluate your expression. So as you can see here, minus x to the power of 5 will still give you minus x to the power of 5. Okay, because the negative, right, you multiply, or rather minus 1 to the power of 5 is actually still minus 1. Okay, so if you want to put this very clearly, you can actually write it this way, which is f of minus x is equivalent to minus x to the power of 5 plus minus x. Then you can see there's a minus 1 here. So minus 1 to the power of 5 times x to the power of 5. So apply the power to each of the term, minus 1 and x, separate it out. So this is obvious, a minus x here. So since minus 1 to the power of 5 is still minus 1, right? So you times x to the power of 5. So minus x. So hence you get the equation minus x to the power of 5 minus x. Okay, and if you compare with this expression here, you can immediately realize that after factorizing out a negative sign, you get x to the power of 5 plus x. So hence, logically, you observe that this guy, right, is actually the minus f of x, okay, which is original function given here. So now, because f of minus x equals to minus f of x, and that actually satisfies the odd function definition, so we have an odd function here. Questions on this first demonstration of the checking whether a function is even or odd, in this case odd? Okay, so graphically, you can of course see this logically as well, because if you look at this expression here, and you try to sketch it out, or you can plot using Desmos. So x to the power of 5 is an odd function that goes this way. Okay, so this is x to the power of 5. And then if you have x, right, x is just a linear function, so maybe it looks like that. So this is x. So you can observe clearly that if you take the sum of these two functions, x to the power of 5 plus x, right, then you are just going to get another odd function. Okay, that is given by the green guy. So this is f of x. Of course, my sketch is not so nice here, but I think you get the idea. Okay, so odd function plus an odd function, right, will give you a resultant odd function. All right, and this is clearly seen from the graph here. Next, we can look at this g of x. So maybe, of course, you can check this mathematically, but however, you can somewhat inspect this and tell yourself that this is actually looking like an even function. The reason is because 1 is a constant. So 1 only moves up minus x to the power of 4 by 1. Okay, so logically, we can observe that graphically, you have, for example, minus x to the power of 4. So minus x to the power of 4 is really looking like that. So this is minus x to the power of 4. And then subsequently, you have a 1. So plus 1, right? It really means you bring up the constant. So let's say this is 1 here. And when you sum them up, you're just going to get a graph that looks like that. So hence, the green guy is actually your g of x. Okay, your g of x here. So clearly, you can see that an even function plus an even function, right, or minus an even function, you get another even function, right? So this is, of course, viewed clearly from the graph. And it will agree with your operation. So maybe let's check through the operation together. So first of all, as usual, we will just sub in minus x into x. So hence, your graph is actually 1 minus x4, 1 minus, so x now becomes minus x, so minus x to the power of 4. So once again, you can observe that this is really 1 minus x to the power of 4 again. because minus 1 to the power of 4 is just give you 1. Okay, since this is an even power. So hence, right, 1 minus x to the power of 4, isn't this exactly g of x? Right? So hence, you get the condition g of minus x is equivalent to g of x. Okay? So hence, even. Function is even. Right? So, and this agrees with the graph shown here. Okay? And lastly, C, h of x equals to 2x minus x squared. Okay? Immediately, you might observe that this guy is an even. This is an even. So even plus even or even minus even, you get even. And correspondingly, odd plus odd, you get odd. Okay? So let me just write this. However, generally, if you have even plus odd or even minus odd, right? Or odd minus even, vice versa, you are going to get a function that is neither even or odd. Okay, and this actually can be clearly seen from the graph. But before we do that, maybe we can check. So we observe that this guy is actually an odd function. And then now you're trying to plus or minus, right? An even function here. Okay, plus or minus. So let me just put a plus or minus here as well. So hence, odd, even, when they are added or subtracted, you will generally get a neither. Okay, so why is that so? Let us show it together. So now we have h of x or h of minus x is equivalent to. So the function here is actually 2x minus x squared. So you get 2 times minus x minus x squared. So 2 times minus x is actually minus 2x. And this is actually minus x squared, but minus x to the whole thing square, right, is still x squared. So now, what is the original function? Original function is 2x minus x squared. Can you actually factorize out a minus and then you get 2x minus x squared back? The answer is no, because the minus is only residing with one of the terms here. So therefore, you can observe that this is neither h of x and is also neither minus h of x. Okay, so it does not satisfy even definition. It does not satisfy odd definition. Okay, so not equal, right? You cannot, no, you cannot like factorize things, right, and try to put it into either of the even or odd forms here. So hence, you have neither even or nor odd. Questions on this operation here, on checking the symmetry of a function? So let me show you the graphical context here. So graphically, we can observe that logically, if you have an even function, for example, 2x, so let's say this is 2x, and you try to minus x squared. So let's say your x squared is, x squared is positive, or rather minus x squared. Let me just do minus x squared. This minus x squared. Now, by purely observation, right, you know that this guy plus this guy, right, is not going to give you something that is neither even or odd. Why is that so? Look at this. This is my negative plus negative, right? Negative plus negative. So you're going to get more negative what? So maybe you get something that looks like that here. Then subsequently, from here, you get negative or you get positive plus negative. Positive plus negative. So I'm not sure. This guy, right, maybe it looks, let me see. Maybe it's something like that here. Okay, so therefore, this is actually your h of x. So it's actually a parabola that is shifted upwards as well as towards the right. Okay, so hence, right, this thing is definitely not odd or even. Okay, because there is no symmetry, there is no reflection, it's offset already, right? There's no reflection about the y-axis. At the same time, you cannot say that you take such a point, right, and then you reflect over to get, you know, some point here, because there's no point here, right? So therefore, it is clearly neither even nor odd. Questions on the checking? So there are really two ways to check, right? One is through the operation, the mathematic, mathematical checking, and the other one for confirmation, you can use the graphics, the graphical way. Okay, of course, to be more, how to say, precise, okay, you have to use the mathematical notation, right? Because graphically, right, it can look like it's odd, but if you go like if you zoom into the curve, right, it may not be odd, right? So because you're just eyeballing it from the graph. So precisely you have to check. So this is what I mentioned. Okay, so after you draw, you will see something like that. So next we move on to increasing and decreasing functions. But before that, any questions regarding to symmetry? So Norofik asks, can you tell a function of an expression by looking at the biggest power of the unknown? The answer is you can look at the biggest power and look at and imagine how the function can look like towards the plus minus infinities. But generally speaking, how the function look like exactly may not be easy to tell because it depends on the complexity of the function. So let's say x to the power of 5 minus x cubed. So if you have y equals to x to the power of 5 minus x cubed. So now we look at this highest power. In fact, we're going to cover this in a while, right? But since you asked, I just give you a sneak preview. So x to the power of 5 here, you can imagine this x to the power of 5 is the dominant. Is the dominant term. Okay, as x goes big, let's say 1 million. 1 million to the power of 5 and 1 million to the power of 3 is what we call an order of magnitude difference. Okay, so eventually as x goes big, right, this guy, the highest power term, will be the dominant term in deciding the shape of the graph. So imagine as x goes to plus infinity, some super big number, x to the power of 5 is positive. So it's going to overpower this negative x to the power of 3. So which means we know that as x goes to positive infinity, you are going to get a graph, right, that goes this way up. Okay, it goes this way up because this guy is also going to positive infinity. Okay, that means y, right, is going to positive infinity because this x to the power of 5 is positive, right? Similarly, when you have x going to negative infinity, then this guy is going to also go negative infinity because of the power of 5. Okay, so minus infinity, imagine, minus some big number to the power of 5, right? You get some super negative big number. So hence, the graph is going to look like that, right? So hence, this is also going to minus infinity for x to the power of 5 or y. So what happens here, right, in the center of the graph, you would have to go through the proper graph plotting procedure. For example, finding the y-intercept, finding the x-intercept, finding the roots, finding the zeros, and finding the minimum, maximum, inflection points, etc. Okay, so you can also look at concavity of the graph, okay, which will be covering in the second term of this course. Okay, do I answer your question, Nurafik? Okay, so whatever happens here, right, you need to really look at the roots of the equation. For example, I can observe here that the roots of the equation here, right, is going to be, let's say if I factorize out, say x, let me see, I can factorize out x cubed. So if I factorize out x cubed, this is really x squared minus 1. So which means that the roots of the equation will be at x equal to 0 because x cubed equals to 0, and then x squared minus 1. So which means that x equals to 1. So these are my roots of the equation. Okay, or zeros of the equation. So which means x goes to 0, which is here, and x goes to 1, which is maybe here, right? The graph is going to intersect. Okay, that means there's going to be intersection. But how the graph behave before and after the root, right? Is it this way or is it this way? Right, we're going to inspect more, okay, by looking at the gradients. Okay, that will come after you have learned how to differentiate a function. Okay. So next we look at increasing and decreasing functions. So increasing and decreasing function, the idea is very simple, okay, and straightforward. So you can see if your graph is raising from A to B, right, then of course the function f is increasing. Okay, and it must be, when we say increasing, right, it must be strictly increasing. Okay, strictly increasing means you cannot say that the function is increasing from A to D because there is a section from B to C, right, that it doesn't conform to the increasing definition. Okay, because it is actually decreasing. So therefore, just look at the graph. You can decide on which interval is it increasing or decreasing. But of course, this is easy if you can look at the graph. Okay. However, if you don't have the graph, then sometimes for simple functions, we can also just look at the function, right, and tell where are the points of increment or decrement. Okay. Of course, the gradient is going to help us as well. Okay, as you'll see later on in the later part of the course. So function f is said to be, of course, a to b, right? You can see a to b. So this is definitely increasing. And b to c is definitely decreasing. And c to d is clearly increasing again. Okay, so just by looking at whether the graph rising or falling. So the increasing function and decreasing function definition, as I have mentioned, has to be strict. Meaning to say, right, the function is increasing whenever f of x1 is less than f of x2, when you have x1 less than x2. Okay, so which means that as you progress from x1 to x2, the graph must rise. Okay, the function value must increase. Okay, so hence you have increasing, and vice versa for decreasing. So I think it's pretty clear here on the definition. So that's what I mentioned, all right? It must be satisfied for every pair of x1 and x2, okay? So correspondingly, if you can look at this, right? So the increasing function here is that f is clearly increasing interval from 0 to infinity, right? So over this part, f of x is increasing, okay? And you can clearly observe this, right? That means no matter what x1 and x2 you choose, you can choose this pair of x1, x2. You can choose another pair of x1, x2. Let's say this is your x1, this is your x2. You can choose another pair. So regardless of which pair of x1, x2 that you choose, right? As long as x2 is after x1, okay? x2 is after x1. And you have f of x1 less than f of x2, or f of x2 is bigger than f of x1. Then you say that the function is strictly increasing over this interval, okay? So that's the concept of increasing and decreasing agreed from the graph. Summary, you can go through yourself. So now we're going to touch on mathematical models. Loosely speaking, these are mathematical models. In fact, they are just elementary functions. Okay, so let me give you a broad idea of why we need mathematical modeling here. So usually, when we try to solve a problem, it comes from the real world, all right? And this can come from your job. Usually, you get employed to solve some problems. And as an engineer, right, maybe they ask you for example, I want to design a suspension system that can cushion the impact of a falling mass. Okay, for example, the safety system that is being used in a lift system. Okay, so if you have the chance to look at lifts, right, the interior of the lift, you might see that there are suspension systems at the ground floor or at the lowest floor, such that in the event of the lift cable snapping and then the lift falls down, right, there is actually a cushioning, okay, of that impact, so that there is less chance of death or serious injuries being imposed on the lift passengers. Okay, so that is actually like a, how to say, accident prevention system. So now let's say you work with Toshiba lift systems, okay, and then you are engaged to design the lift system, design the lift suspension safety system, and in order for you to do that, right, you got to know the mathematical so-called variables. Okay, for example, what is the maximum speed that you want the suspension system to withstand? Okay, because the maximum speed that you design the lift falling for has actually influence on the type of springs, okay, and dampers that you use. So therefore, there are parameters and there are variables. Okay, so it comes from a real world understanding of the problem that you want to solve. Okay, for example, in this case, designing a lift safety system. Now, after understanding the real world problem, right, now you need to build a mathematical model. Why I say that is because imagine now you try to design a lift spring system, or a mass spring system. Okay, so a platform here. So imagine now the leaf is falling. So a mass is falling. So this mass, which is representing the leaf, is falling, and it impacts this suspension system that you are trying to design. Okay, so now of course you have design parameters. For example, the maximum acceleration or maximum deceleration applied to the mass, or maximum jerk applied to the mass, right, cannot be more than a certain value, or else the passenger will die. Okay, which means that can suffer serious injuries to the neck or spine. So therefore, now, what is your mathematical modeling part here? Now, you want to know, right, what is the response of this mass? So when this mass actually impacts on the suspension system, you can imagine this mass, right, is going to compress. Okay, it's going to compress this suspension system, and it might be going through some kind of vibrational motion. Okay, it might be going through some kind of vibrational motion. So this can be the displacement, let's say y of t, and this can be the time t. Okay, so you want to solve for y of t, which is, for example, you want to solve for y of t. So in this case, it should be negative. So let me just make it more logical. So because when it impacts the system, it's going to compress, right? So you're going to shoot up, right? So maybe once it compresses, it's going to shoot up and then it maybe vibrates a bit. So hence, to design this system, right, obviously this system is going to be dependent on the spring stiffness, the springs that you choose, as well as the damping coefficients, that the damper that you choose. Okay, so therefore, now in this respect, right, you are interested in, for example, selecting proper springs and proper dampers such that your passengers will not get killed or suffer serious injuries according to the design of the lift system. Okay, so hence you need to solve for the mathematical model. You need to model this problem mathematically first before you can even solve for this y of t. This y of t is a function. It may be a sinusoidal function. It may be an exponential function. Okay, so that depends on whether what are your k and c's. Okay, so hence, right, to get the mathematical modeling part, you have to apply a certain set of rules or laws to this problem here. Okay, so this problem can actually be defined, right, by the summation of f equals to my double dot. Okay, so this is usually just Newton's second law. Okay, y equals summation f equals to ma. So if you apply summation f equals to ma to this suspension problem here, you are going to get a differential equation. Okay, so a differential equation, right, is not giving you this y of t first. It's not giving you this y of t yet, right? Then you have to solve. So you solve for the y of t. Now, when you solve for this y of t, you will know how the suspension system responds. Okay, how this wave actually looks like. Then from the wave, you can actually derive the acceleration as well as the jerk from this function. Then subsequently, you are going to interpret what is this and see if the k and c that you choose, right, are satisfying your real world conditions or requirements, okay, of keeping the lift passengers safe. So therefore, this is the entire process, okay, of doing, for example, an engineering design, okay, of an engineering system. So therefore, mathematical modeling, right, is actually quite a big deal, okay, and it forms, how to say, the crux of why you study so much mathematics. So now you are just at the function part. You study functions, later on you will study mathematical modeling or differential equation. So in the process of solving the differential equation, you will need to know integration. That's why the integration comes in. Okay, so MAT 150, right? So I'm trying to give you a big picture now. MAT 150, you deal with differential calculus. MAT 200 will deal with integral calculus. MAT 256, you deal with differential equations. Okay, so therefore there's a lot of math that goes into engineers here. Okay, engineering systems here. So there are some other examples here, right? That I'll leave you to go through. Right here, we just look at the various functions because we're still doing a review here, right? So we look at the various functions that can assist us in describing the real world phenomena. For example, the suspension system response here. And right here, right, we are going to look at the characteristic of the different functions. Okay, there can be linear functions, quadratic, exponential model, polynomial functions, trigonometric functions, etc. Okay. So today's maybe objective is I will try to finish up to maybe the trigo functions. Okay, so just slow me down if I'm going too fast. So next we look at linear functions or linear models. So linear function is really the simplest. I mean, the simplest function is actually a constant. Okay, y equals to c. So maybe a linear model is the second simplest function, y equals to mx plus b or y equals to mx plus c. So the formula for the function, right? I think you have definitely seen this before, y equals to mx plus b. And this is what we call the slope-intercept form. So slope-intercept form is quite clear because this is really just slope, which is given by m, and then the intercept, which is given by b. So obviously this intercept will be the y-intercept, okay? So having the slope-intercept form of a linear function, there are other forms of the linear function as well. So, but before we look at that, right, you can imagine that why is this linear? Okay, the reason it is linear is because, right, of this mx here. Okay, plus minus b, right, plus minus b basically just shift up or down the function, okay, the line. So, for example, we can clearly see that plus b here for the blue line, right, and you can get b by simply substituting x equals to 0. So quite obviously, to get b, you just let y equals to, or let x equals to 0. Because let x equals to 0, right, will be exactly at the y-axis. So that is why b is known as the y-intercept, because you are looking at the point, right, whereby the function intersects the y-axis. So therefore, y of 0 is actually just equals to b. Okay, so hence the y-intercept. And at x equals to 0, which is the y-axis, so we can observe that this guy is b equals to minus 3. Okay, so hence you have a minus 3 here, right? So the slope, of course, we have dealt with how to find slopes already. Okay, so it's just taking the change in y over the change in x. Or did we go through that? Oh, it looks like we have not gone through that yet. Okay, that's for another course. So, but regardless, the slope m, right, is just given by, for example, you can choose any two convenient points to calculate your slope. Okay, so right here, I'm just going to maybe choose, let's say this minus 6 looks like a nice point, and maybe this 0 here looks like a nice point as well. So therefore, I can just form a triangle, and then I just do my delta y is equals to what? So what is the change in y? So obviously a change in y here is 0. This is y equals to 0. And this is y equals to minus 6. Can you look at the minus 6 here? So hence, right, the slope m here will be change in y, right? Which is 0 minus minus 6. Okay? So it's actually, let me just write this properly. So hence this guy, right, I can call it x2, y2. And then I call this x1, y1. So whichever you label as 1 or you label as 2 does not matter. Okay, so it's going to just work itself out correctly later on. So let me write down the general formula for this. This is really change in y. Change in y. Let me use a different color. Over change in x. So this is my change in x, which is over here. So change in y is y2 minus y1. So y2 minus y1 over the change in x, x2 minus x1. Okay, so as I mentioned, it doesn't matter which one is 1, which one is 2, right? But it must be consistent. If you have 2 minus 1 for y, you must have 2 minus 1 for x. Okay, if you have 1 minus 2 for y, you must have 1 minus 2 for x, right? So do not swap the numbers anyhow. You must be consistent. So hence, after you have this, right, then you can clearly just fill in the blank. So as I mentioned just now, y2 is 0, y1 is minus 6, and followed by x2. So what's x2? x2 is actually, look at this, it's x2. So x2, right, is actually 6. Then x1 is actually minus 6. So it's actually minus 6. Is that right? So hence, we can observe that this is really plus 6 over 12. Okay, so hence this is a half. So the slope is half. That's why you get this half slope here. Is that all right? Okay, so obviously I choose x1 and y1. I choose point 1 and point 2, right? Being the points here respectively. You can choose any other point. Okay, you can choose any other 2 points, in fact. So as long as they are not the same point. So you can repeat the same for the red line. and you'll be able to get the slope, which is -1. So obviously this is wrong, right? How can this be x? Observe that. Okay, so this 5 is correct because I can clearly see that my y-intercept here is actually 5. All right, so b equals to 5 here. So what is wrong with this guy? This is actually a negative slope. Okay, because your y is actually going down, right? That means as x increases, your y is dropping. So hence, this slope, right, is going to be a -1. Okay, so this is actually -1. So hence, this is actually a negative here, right? So there's an error here, a typo error here. So the y-intercept is clearly just 5. Okay, b equals to 5. Questions? So I hope this is just a simple recap of what you know about straight lines or straight line functions. Okay, move on. So the characteristic of linear models, right? And why are they straight line? As I mentioned just now, is due to this mx. Okay, and why is that so? Because, right, this mx is telling me y equals to mx. B is just shifting it up and down. But y equals to mx is telling me, right, for every increment in x, there is a corresponding increment in y. Okay, I repeat again. For every increment in x, there is a corresponding proportional increment in y. Okay, so therefore this is called linear. So linear means, right, y equals to mx, and this m, right, is a proportionality constant. So y is proportional to x by m. So this is called proportionality constant. Okay, also known as the gradient, right? So I believe you have heard of like y equals to kx. So y is proportional to x by the constant k. So we just use m here in this case. Okay, so just now I mentioned m more than 0, graph will rise. M less than 0, graph will fall. Okay, as you progress in the positive direction of x. And m equals to 0 and line is horizontal. And this is pretty clear, right? Horizontal, you get 0, right? The reason is simply because change in y over change in x, right? Then you have a change in y equals to 0, what? 0 over some positive change in x. So hence this is 0, okay? Because for horizontal line, you can imagine that y1 and y2, right, are exactly the same. So let's say this is 0.1, this is 0.2. So you can clearly see that you have y1 equals to y2. Okay, so y1 equals to y2. Okay, exactly horizontal. So hence the change in y is definitely 0. So I mentioned about calculating m already, right? You can choose any 2 convenient points and you will see that your gradient will be the same. Okay, but just make sure that I keep emphasizing this. Do not swap these numbers anyhow. 2 minus 1, 2 minus 1. 1 minus 2, 1 minus 2. You'll get it correct. Okay, but do not have 2 minus 1 over 1 minus 2. Okay, then it's wrong. So slope-intercept form we have gone through already. Then you might have heard of the other form of the equation, which is the point-slope form. So the point-slope form, right, is actually taking, for example, so this guy, you can see that this is y minus y1 equals to m x minus x1. Okay, so if I treat f as my y, so this is just equivalent to y. So y minus y1 equals to mx minus x1. But if you look at this, right, and you rearrange it, isn't this the gradient equation? So this actually comes from the gradient equation, y minus y1 over x minus x1. It's just that in our gradient, right, we label one of the points as point 2, y2 and x2 respectively. But there's no need to do so, right? You can even just choose any general point, y and x, that is not at y1 and x1. And you will be able to calculate m here. So therefore, if you choose y and y1 and x1 as your 2 points in your gradient, so let's say this is x1, y1. And this general point is actually xy. Okay, so xy, right, can shift. You can shift this point around. Okay, you can shift this point around. As long as it's not at x1, right? You will be always able to calculate this constant gradient m. Okay, so therefore, you just rearrange the equation by the definition of the gradient, you get the point slope form already. Okay, so you can see these two are actually related. How is the relation? Notice that from here to here, right, you just have to have your x1 being 0. So if I choose x1 equals to 0, y1 equals to b. Okay, so what is this? This is actually at the x-axis. Oh, sorry, at y-axis. Okay, because y equals to b is your y-intercept, what? All right. Okay, x equals to 0 is here already. So therefore, right, if you have something like that, then you know that this is just f of x minus b equals to mx minus 0. So isn't this f of x equals to mx plus b? Okay, that goes back to the slope-intercept form. All right, so they are all correlated, and it really just comes from the definition of the gradient here. Okay, so finally, you can have a third form, which is the standard form of a line. Okay, so ax plus by equals to c. So in case you do not believe that this is actually giving you a straight line as well, you can clearly just check in Desmos. Okay, so for example, I say 2x plus 3y equals to maybe 1. So you can see you have a straight line here. Okay, and the 2, 3, and 1, the a, b, and c's, right, are actually correlated. Okay, hold on, let me see. Right, not correlated, but can actually be worked out, okay, from the gradient as well as the y-intercept. Norofik asks, can you repeat slowly for the point-slope relation? Sure. So point-slope relation comes from gradient. Okay, so this one, right, is actually from gradient formula. So we can see it here, right? Isn't this a gradient formula? This is my gradient formula. Okay, so just now what I was saying is you can choose any point xy. Let me just draw this clearly. I'm rushing a bit today because actually I have quite a bit to cover. So let me show you this point. Okay, so let's say this point, right, you choose as your xy. So this point, like a slot, you can move one. Okay, you can shift it around. Then you choose a fixed point, x1, y1. Now you think about it, the gradient is constant, what? So it doesn't matter if this green point is here, or this green point can be here, or this green point can be here, can be anywhere. So that's why I say xy, right, is variable, right? You can switch around. However, as long as you don't choose this point exactly the same as x1, y1, you will be able to calculate this gradient. Or else you get 0 over 0, and therefore indeterminate form. Okay? Because if you choose xy to be x1, y1, right, that means you choose the green point exactly at this point, then you're in trouble because you get 0 over 0, indeterminate form. Right? And we're going to deal with that in limits later on. However, at this juncture, right, understand that when you shift xy, as long as you don't go to x1, y1, you can calculate the same gradient m. Isn't that correct? So therefore, this m, right, given by this equation, right, whereby you have x and y as variables. So you can rearrange. So rearranging, you get this guy, right? But isn't this guy exactly the point-slope form equation? It is, right? Okay, so that's the derivation of this point-slope form, okay, from exactly the gradient m formula. Now, what is the relation here? Now you can see that if I choose x1, because x1 and y1 are arbitrary points, okay? x1 and y1, right? No, because x1 and y1 is up to your choice, okay? Where is the so-called pivot point, right? It's up to your choice. So therefore, if you choose x1 to be 0, choose x to be 0, choose x1 to be 0, which means, right, I practically just fit x1, y1 to be at my axis. Okay, so if you have x1, y1 exactly at the y-axis, by choosing x1 to be 0, and y1 is what? y1 is b what? Because y1 is the y-intercept in this case already. So isn't this B? So y1 is B. Then you just substitute in, right? Substitute 0B into this equation, rearrange it, and you get the slope-intercept form. Do you see that? Okay, because point-slope form to slope-intercept form is just by choosing point x1, y1 exactly at the y-axis. Norafik, is it okay? Okay, so I think you go through this again, right? So this part is actually nothing, no big deal, just direct substitution. Can see after I choose x1 equals to 0, y1 equals to b, then I just substitute, direct substitution only. Okay, then you get this one. But what is this one? This one is this one. This one is this one. Okay, so it's all related. It's all like, you know, multiple perspective of the same expression, of the same thing, which is a straight line. We should ask, do we have to know what each form is exactly, or we just need to know how to derive the various forms? You don't need to know how to derive, but you need to know, yes, there can be a question that we ask you for a specific form. However, the context here is, it depends on what I give you. Okay, it depends on what I give you. So which means if I give you 2 points, x1, y1 and x2, y2, then I ask you to give the point slope form. You must be able to translate from that 2 points on the line into any of the form here. Sorry for the disturbance, fighter jet. Okay, let's continue. So the question can be, right, it depends on what I give you. If I give you the gradient, hold on. Okay, sorry about that. Right, so if I give you the gradient and maybe 1 point, then I ask you to give me, for example, the standard form. You must be able to do that as well, right? So it depends on what is the 2 pieces of information you are given and what is the required equation of the linear function that is being asked. Okay, so you are able to translate, right, between what is given and what is the linear equation in any of the 3 forms there. Okay, how to derive, you don't really need to know how to transit between each of them, but you need to know how to translate from the given information to the linear equation. Okay, so yeah, so let me explain this standard form of a line again. So if you look at this expression, right, actually you can just, you know, mess around with this expression a bit, like manipulate it. So look at this, this is actually just by equals to ax or minus ax plus c. You see that? So they just bring ax across, no big deal with that. Okay. So, but I want to get, let's say, for example, the standard, the slope-intercept form. Slope-intercept form, you can see y is equal to minus a over bx plus c over b. How about that? Okay. So let me just let me just do an example here. Okay, let me just do an example here. So just now, right, you can see that in decimals, I actually have 2x plus 3y equals to 1. 2x plus 3y equals to 1. So let me just give you an example here. Let's say 2x plus 3y equals to 1. So 2x plus 3y equals to 1 is what? So it's like a equals to 2, b equals to 3, c equals to 1. Okay, just read off this directly. And now you want to work out what is the m and b here. Okay, this b is different from this b, yeah? Okay, just that they use the same stuff. So therefore, you can see that to get the slope-intercept form, I have y equals to minus 2 over 3 x plus 1 over 3. Minus 2 over 3x plus 1 over 3. I get the slope-intercept form already, right? And how do I check? I can verify it graphically, right? Minus 2 over 3x plus 1 over 3. So let me just plot another function. Y equals to minus 2/3 times x plus 1/3. You can see that both lines are exactly coincidental. You see that? Hold on, let me just make this projector mode so you can see clearer. How about that? Okay, they are exactly at the same line. So hence, right, you're able to transit between slope-intercept form and standard form easily. Okay, so if you want to transit between slope-intercept form to point slope, then you use this, okay, expression here, or you use this procedure here. All right. Okay, so this is an example of a question that you might get. Okay, so you are given some information, then you got to put it. So this is the real world problem, okay, the real world information. Then you got to put it in a mathematical expression, okay, for example, a linear expression. So let's do this together. So we have as dry air move upwards, it expands and cools. If the ground temperature is 20 degrees Celsius and temperature at a height of 1 kilometers is 10 degrees Celsius, so I express the temperature in degrees Celsius as a function of height. So this statement effectively tells us that we must have height at the x-axis and T in degrees Celsius as the y-axis. So this is km. So assuming that a linear model is appropriate. So therefore, we can see that at the ground, right, is actually 20 degrees Celsius. And then you have 20 and 10. So I'm just going to put maybe 20 here and maybe 10 exactly at half. So hence, right, this is at 0 is 20. So where's my point? My point is actually this point. This is one of my points. And another point, right, is at at h equals to 1 kilometers. So let's say 1 kilometers is somewhere here. Okay, this is 1. So therefore, I'm going to have another point at 1 kilometers and 10 degrees Celsius is another point. So what is the information? The information is 2 points on the graph. Okay, 2 points on the graph. So therefore, right, we have to express this function now. So assuming that a linear model is appropriate, express the function t, express t as a function of height. Okay, so they never say which model that you can use, or rather which form you want to use. So we can just choose a convenient form. So hence, right, this guy probably looks like that, since you have a linear model. Okay, I mean, not very accurate, but I think you get the idea. So what is the equation? So now you want t is equal to, so t as a function of h is equals to mx, so mh plus c. So c is a y-intercept, okay? Or rather mh plus b lah, since they use b. So b is clearly just 20 because at h equals to 0, because ground is h equals to 0. Okay, let's assume that at the ground. So therefore, this b is just 20. Okay, this b is just 20. So we know that this is 20. However, we need to get the m. But you got 2 points, what? So 2 points allow you to get this m easily. So therefore, the gradient, right, can just look at this triangle here. Nice triangle here. So therefore, the gradient m is just equals to 20 minus 10 divided by 1 minus 0. Oops, sorry, it should be 0 minus 1. Okay, because I take this point minus this point. So hence, right, I should get minus what? 20 minus 10, 10 divided by minus 1. So it's actually minus 10. Okay, so this will be minus 10h plus 20. How about that? Okay, and you can test a few points, right? For example, at h equals to 0, t equals to 20, check. At h equals to 1, minus 10 plus 20, so it's plus 10, check. You can see that? So your equation must clearly satisfy the 2 points that you use to get the gradient. Questions? So it's just about finding gradient and finding y-intercepts. So that's for part A. And for part B, draw the graph. So this is done already. So what does the slope represent? So it is quite important to interpret the slope here. Right here, right, I did not plug in what is the units. But if you plug in the units, the slope will become very clear. Okay? So check. What is this 20 minus 10? It's the difference in degrees Celsius. So therefore, this is degrees Celsius over. What is this 0 minus 1? Change in height. Okay, change in height. So therefore, this is kilometers, height in kilometers. So hence, what does this slope represent? Change in temperature per kilometer traveled, right? I repeat again, change in temperature per kilometer increase in height. So let's write it down. The slope represents change in temperature in degrees Celsius per kilometer or per height increase in kilometers. Okay, so in the layman, right, it means as you move up 1 kilometers, what is the change in temperature in degrees Celsius that one can experience? Is that right? Okay, so the slope is not just a number, right? It's actually having some physical meaning. Okay, so it's actually minus 10 degrees Celsius per kilometers. Okay, for this slope M here. So after you get the expression, right, you can actually do what we call predictions already. Okay, although you have just 2 points, but because you assume a linear model here, so hence you are actually able to do predictions, okay, using this linear model, right? Of course, your linear model may not be accurate, right? Since you have only 2 points, right, and the graph can actually change in this way. So it can be other forms of model. It might not be a linear model, okay? But of course, to have verification of your whether your model is accurate or not, you definitely have to be more. You definitely have to get more than 2 points. Okay, the more points you have, the more accurate a model, right, that you will be able to construct. So therefore, let's use our linear model and analyze what is the temperature at a height of 2.5 kilometers. Okay, so 2.5 kilometers, that's quite straightforward. So it means that h is 2.5. So since you have your function already, you're just going to calculate t at 2.5 is hence equivalent to minus 10 times 2.5 plus 20. Okay, so just using this linear model here. So clearly this is minus 25 plus 20. So hence you'll get a negative 5 degrees Celsius. Okay, so I think from here it looks pretty legit here, right? Because 2.5 is maybe somewhere here. Okay, 2.5. So you get a negative temperature. Questions? Looks good. So we're done with this. So you can see here that if there's no physical law or principle, like just now I mentioned that we can actually model things from applying Newton's second law, right? And there are many other laws that we can apply. A few of which are conservation of energy, conservation of mass, conservation of momentum is effectively Newton's second law, conservation of charge, okay, conservation of species, right, in chemistry. So therefore, all these, right, conservation laws are commonly used, right, to construct the model, okay, the theoretical or the analytical model. However, in some cases, right, there can be either no physical law or principle, or the physical laws and principles involved, right, are too complicated. That means there are too many effects that causes the output to change with respect to the input. So there are many. So hence, right, if that is the case, right, then we can depend on what we call an empirical model. So an empirical model is something like, for example, okay, let's say you have a few points, right? And let's say this is your data. So maybe your data looks like that. Okay, and now you want to have this empirical model that fits all these points as best as possible. Okay, as best as possible. So hence this is called an empirical model because, right, you are actually just trying to curve fit through the actual points or actual data points that you have collected, okay, without understanding what actually goes on behind the scenes. or what is the reasoning for the output to change with respect to the input in this manner. Okay, that means you do not know actually what is causing the change or what is causing the behavior, right? You just want to get this function experimentally. Let's say y is a function of x, experimentally. So empirical, right, is also like experimental, okay? So before we go into polynomial functions, I think maybe it's a good time to have a short break. So let's break for 5 minutes. So Nicole is asking, is the empirical model a best fit line? In fact, empirical model is a good question. Best fit line can be two best, meaning to say what we call overfitting. Okay, what we call overfitting. Let me give you an example. So for example, let's say I'm trying to predict housing prices. Okay, let's say this is the price of a house, okay, in dollar, for example. And then let's say this is the area of the house. So of course, we can use actual data, which is like actual transaction, right? Because you go to like Property Guru or, you know, some so-called website that captures property prices. Then you probably can see a trend maybe that looks like that. So more area typically will give you more higher price. Okay, maybe it looks like that. So now you try to do a best fit line. Okay, but there are many ways to do a best fit line because best is subjective. How best is subjective. So one can say that, well, a best fit line maybe looks like that. Okay, so this model, maybe you use a logarithmic model or you use a quadratic model. Okay, so the model, of course, is dependent on the data analyst, for example. So hence, this can be a good model. Then, but if you look at this model, right, then one can argue that, hey, this is the actual transaction. For example, this is the actual transaction, transacted price, okay, given this area. But your model has an error because look at this error. This is an error, right? Isn't this an error? So this is an error from the actual transaction to your best fit, so-called best fit model line. So hence, right, is this the best model line? That may not be the case. Then another so-called mathematician or, you know, data analyst, right, can argue that, well, I can have an even better best fit line. So maybe the best fit line, I try to curve it through the points in this case. Okay, a very curvy curve, but they try to curve it through most of the points so that they reduce this error. Then this is another best fit line. So how best is best, right? So of course, how best is dependent on certain recommendations, okay? But what I'm trying to say here is that it also depends on your perspective, okay? Now, typically, right, in data analytics and machine learning, this is called overfit or over best already, overfitted model. It means the model does not capture the general trend, but instead try to go through all the transacted points exactly. Okay, and this wouldn't be good. This wouldn't be good because typically, right, a good model will try to capture, like for example, this line here, right, will try to capture the general trend of the price versus area relationship, for example. Okay, so a best fit line is correct, generally is correct. But how best is best, right? There is actually some mathematical definitions. There is also some so-called subjective viewpoints. Did I answer your question, Nicole? Okay, very good. So if you want to know the mathematical viewpoint, right, is that typically we want to minimize this error. We want to minimize the sum of the square of these errors. Okay, this is actually one of the techniques in machine learning and in linear algebra. Okay, so which I'm not going to go through here, it's a bit you know, over the place. So hence, yeah, just it looks like we have just 1 more minute. Okay, so just take a short break, have a drink. So let us continue. So now we look at polynomial functions. Polynomial functions, polynomial, right? Poly means like many. So this is really just many. And then this nomial means terms. So polynomial in layman, right, is just like a function that consists of many terms. Okay, and you can see it from here. For example, generally a polynomial, right, is given in the form of, for example, ax to the power of n plus n minus 1 to the x power of x minus n minus 1, so on and so forth. But generally, let me just write it nicely here. So it's just ax to the power of n. Okay, let me give you an example. So it can be ax to the power of 5 plus bx to the power of 4 plus cx to the power of 3 plus dx to the power of 2 plus ex to the power of 1 plus maybe f. Okay, so a, b, c, d, e, f, right? Those are just constants, or what we call coefficients. Okay, coefficients of the polynomial terms. So what is this? This is called a fifth order or fifth degree polynomial, because the degree of the polynomial is just the highest number, highest power. Okay, so therefore this is polynomial of degree 5. All right, so this is just like jargon, okay, some definitions. So polynomial of degree 0 is constant because x to the power of 0. Okay, so for example, if you have p of x is equals to ax to the power of 0. Okay, since you have only just one term, so hence this is really equals to a. So a is a constant. Okay, so polynomial of degree 1. So you have ax to the power of 1 plus b. So hence you get mx plus b. Okay, so it's a linear function. Degree 2, can see quadratic function. Degree 3, cubic function. Degree 4, quartic function, and so on and so forth. Okay, so there's just names given maybe to the first few degree of a polynomial. So a quadratic function will always look like a parabola. So parabola, right? Just a fancy way of saying like you get a smiley face or smiley curve or a sad face or a sad look here. So whether it is smiley or sad, right, entirely depends on the coefficient a. So you can look at this guy. So this ax square, this a here, right, you can see that a equals to 1. So because it's 1 times x squared, right? Okay, this a here. So ax squared. So you have a equals to 1, right? And a, when it's more than 0, you will get a smiley face. Okay, you'll get a smiley face or smiley mouth. Then for a equals to minus 2 in this case, and you have this a, right, being negative, then you get a sad face. Okay, so you have a sad mouth in this case. So why is that so? Actually, I explained this when I think Norafik asked the question about can you actually sketch the function, for example, x to the power of 5 minus x cubed? Okay, we can observe that the dominant term is the one with the highest power. So hence, right, x square is dominant here. Okay, this is dominant. So when this is dominant, right, think about that. Now, when you have x going to plus minus infinity, this x square is going to be plus minus infinity respectively as well. So x positive, x square even more positive, right? So hence, right, you're going to get this way, going to plus infinity as x goes to plus infinity. Correspondingly, as x goes to minus infinity, your x square or ax square is going to go to minus infinity as well. Oh, sorry, plus infinity. Okay, it's still going to plus infinity because you have a square term here. So minus infinity square, right, you get plus infinity, right? Conceptually speaking, of course. So therefore, you get a smiley face. Okay, both ends, right, must go towards positive infinity. So the same can be said for a negative coefficient a. Okay, because this is negative and this is always positive. So hence, right, you always get a negative dominant term. All right, so therefore you get minus infinity, going to minus infinity on both sides. Okay, so hence accounting for the sad face. So there's actually a technical name for this, which I'll cover later on. Okay, this is called concave up and this is called concave down, right? But we'll look at that later on. So cubic functions, right? So cubic functions look like that, right? So the higher degree of the function that you have, right, the more curvy it is. Okay, the more curvy it is. However, the end behavior is still determined by the highest power, the term with the highest power. Okay, so x cubed is similar to x5. If you remember, if you observe, you can see that this is going to positive infinity. This is also going to positive infinity, negative infinity, negative infinity. Okay, for the same reason that I explained just now. Okay, because degree 3 or degree 5, when you give it a positive number, right? Positive x cubed or positive x5 give you positive. However, negative x cubed or negative x5 will give you negative, right? So hence, you have this shape. Okay, but what happens in the center? You have to analyze the gradients, the zeros, the intersects, and so on. Okay? So this example, I think it's a good example to answer Nicole's question, because Nicole asked, is the empirical model a best fit line? Okay, so I'm just going to show you how we can produce an empirical model, and then also maybe try out different fits to the data set, okay, to the data points. So now, we have an example here that shows that a ball is dropped from an upper observation tower 450 meters above the ground, and its height is actually recorded at every 1 second interval, as shown in table 2. Okay, so we just assume that there is actually no physical law or principle that helps to so-called model this. In actual fact, there is, okay, because this is nothing but just a ball, right, being dropped from some height. Okay, a ball that is being dropped from some height. So therefore, this is actually subjected to two effects. One is gravity, the other one is air resistance. Okay, gravity is straightforward. However, the air resistance can be difficult to model. All right, so hence, right, let's assume that an empirical model is necessary here. So what I have done is I have entered the graph in Desmos already. Please, if you have not registered yourself for free in Desmos, get a free account, please do so, because you can save all your graphs in Desmos. Okay, you can see I have many graphs here, right? So whatever graph you have, right, you can save it and then you can, refer to it later on during your revision or during, other courses, etc. Okay, so you might have your own investigation in other subjects or your course of work that you want to do as well. So I've done the I've done the fitting here already, but okay, let me just remove the fitting and just show you the table here. So what we observe here is that this data set, right, is already plugged into Desmos already. So I believe I have showed you how to enter a table. Okay, just plus and then table, right? Then subsequently you can change the variable names here, right? Originally it will be x1, y1. But I'll just change it into T and H to represent table 2. So therefore, you can see time varies from 0 to 9. Height varies from 450 all the way to 61 here. Okay, so I think I did not enter anything wrongly. You can check for me. So after you have entered the function here, now you want to do a fit. So there are many ways to do a fit, as I answered Nicole's question just now. Okay, you can do a linear fit, right? Because if you do y tilde, so this is doing a so-called best fit line now. Okay, so let's have a linear fit. So maybe I call y1. So y1 is linear fit, let's say of a polynomial order 1. So hence I have y1 tilde, right? Let's say, for example, mx plus c. Okay, or generally just make it ax plus b. It should be at then. Sorry, I should give it h1. Okay. Okay, let's give it h. Let's give it h. So h is actually modeled by at plus b. So you can see this is actually a linear best fit line. Is this a best fit line? I can tell you it is really best. Okay, because it minimizes the error, right, between the actual points and the predicted model curve or the model line. So therefore, it is a best fit line if you use a straight line or you use a linear model. Then it is really the best. Okay, but as you can see, this linear fit is not very good. Okay, it's not very good because, well, at this point and this point, maybe it fits the data pretty well. But however, at this point and maybe in the intermediate points here, as well as the end points here, it does so very badly. Okay, so a linear fit is not good. So, but we can, of course, increase the order. So let's have a t square. Oh, by the way, you can see that the fit here, just go back to that fit again. You can see that the r square is actually 0.9. And 0.9 is pretty okay. It's pretty okay, but it's not that good. Okay, 0.92. So let's have a better fit by increasing the order. So maybe at square plus bt plus c. Okay, so you can see here that if I use a quadratic model, it really fits this data set really well. Okay, so of course this is by coincidence, just that this data points, right, are selectively chosen such that it will fit a quadratic model very well. Okay, so you can see r squared is equals to 1. When r squared is equals to 1, it does not mean that it fits the points perfectly, right? It just means that it is able to account for the variance in the data completely. Okay, if you don't understand that, it's fine. We are not going to go into the statistics here. But I mentioned before that r squared closer to 1 means a better fit. Okay, the closer to 1 it is, the better fit it is. So if it's at 1, right, it's pretty much the best fit that you can have already. Okay, so if you try to increase the polynomial order further, you will not get an even better fit. Okay, so let me show that to you. So let's say we have at cubed plus bt squared plus ct plus d. So you can see you still get the same fit already. Just that your a, right, look at the coefficient of a, minus 0.01. So this coefficient of a is much smaller as compared to b, c, and d. So a might as well be 0. Okay, so increasing the polynomial order of the fit does not increase your accuracy already. Okay, I hope you observe that. Okay, because your r squared is already at 1 in a quadratic model. So a cubic model doesn't do you good. Okay, and you can see that, you can verify that because a is so close to 0. So you might as well remove this term. And indeed, we can do that. Okay, so just by having a quadratic model, right, you can really get a very good fit of the data as observed visually, as well as looking at the r square statistics here. Okay, so what are and why do I say that this thing doesn't fit it exactly? Well, it doesn't, because observe that what is the value of the y-intercept d is 449.3. Y-intercept is 449.3. That means this point on the blue curve is 449.3, right? However, what is the actual point at the y-intercept? It's actually 450. Observe that. Okay, so if I zoom in, right, I think you probably can see the discrepancy. Let me try to zoom in a bit. Okay, can see the discrepancy, right? So I wouldn't say it's a perfect fit, but it accounts for the trend effectively. Okay, so that's why your r square is actually equivalent to 1. Okay, so therefore, we have already found our model already from Desmos. And the model is really just the equation that we saw just now. Okay, so I'm not going to plot it here. Okay, let me give the quadratic formula. The quadratic formula looks like minus 4.9. So I'm just going to round off to maybe 2 decimal points or 1 decimal point. So we have minus 4.9 t squared h of t is equals to minus 4.9 t squared. Then our CT is 0.96. So I'm just going to stick with 0.96 t plus 0.96 t. Then the y-intercept will be 449.4 plus 449.4. Okay, so this is actually your quadratic formula. Is that right? So then we can use this, right, to answer the question, when does the ball hit the ground? Okay, so the ball hits the ground when H is actually equivalent to 0. Okay, when H is actually equivalent to 0, right? Because H equals to 0 is the ground. So hence, right, if you substitute H equals to 0 here, you'll be able to solve using your quadratic root formula. Okay, so therefore, I think I'll just leave this for you to try out yourself. So minus 4.9t squared plus 0.96t plus 449.4 equals to 0. So what is t? T is equals to minus 0.96 plus minus square root b squared minus 4ac, 0.96 squared minus 4 minus 4.9 times 449.4 divided by 2a. So 2 times minus 449, minus 4.9. Okay, so this is the quadratic root formula. So you can calculate that. Okay, and then verify with the graph. So I can share the graph with you in MS Teams as usual. Questions on the concept here that you do a fit and then you use the formula to solve for unknowns. Any questions? Looks good. So let us continue. So we have looked at an example of a polynomial function, which is the quadratic function. And now we look at power functions. So power functions are just individual terms of the polynomial functions, okay? Because it's just x to the power of something, right? So therefore, this a here is actually called the exponent, right? And be careful, a power function is not an exponential function. Okay, we're going to cover exponential function in a while, but let me just write a note here because when you revise, right, this is not the same as exponential function because it looks kind of similar. Exponential function, right, will have your variable at the exponent. So f of x is equals to a to the power of x. So when the variable is at the exponent, it's known as the exponential function. However, when the exponent is a constant, then it's just a power function. Okay, so hence when you have many power functions concatenated together, right, then you get a polynomial. So power functions, we have looked at several of these already. Okay, so y equals to x, x squared, x cubed, x to the power of 4, x to the power of 5, and so on and so forth. So general shape looks similar when you have all powers being even or odd. So you can see x cubed looks very similar to x5. X squared looks similar to x4. Okay, so basically the shape of the curve, right, is determined by whether the power n here is even or odd. You can see n is even and n is odd, right? So of course we have odd and even functions correspondingly as well. Okay, because this is an even function because symmetry about the y-axis, odd function because rotation 180 degrees about the origin. All right. So there's a note here. It says that as n increases, right, the graph of x to the power of n becomes flatter near 0 and steeper when modulus of x is more than equals to 1. Okay, there's a good reason why. I hope you can kind of like understand this. The reason is because if you have near 0 means what? Near 0 means, like for example, this point is a decimal. Okay, when this is a decimal, right, when you cube or when you raise it to a higher power, the number becomes smaller. Okay, the number becomes smaller. So let's take a point here as an example. So you can observe that, let's say at x equals to, let's say this is 1, right? So I'm just going to say like this is 0.5 here. So check, this is 0.5 to the power of 5. This is 0.5 to the power of cube. So which one is bigger? Of course, right? X to the power of cube will be less than x to the power of 5 because this is 0.5, right? Because x to the power of cube here, right, is actually 0.5 times 0.5 times 0.5. This is 0.5 cube, right? However, this 0.5 cube, right, is going to be bigger than 0.5 to the power of 5 because you times the decimal more times what? 0.5 to the power of 5 is going to be less than 0.5 to the power of cube. Okay, remember power of 5, right? You multiply by the decimal more times. So hence it is smaller. Okay, so this is the reason why x to the power of n, right, becomes flatter near 0. All right, and steeper when you have transition after x equals to plus minus 1. Okay, and this becomes steeper. Logical reason is if you have, let's say, for example, 2. So 2 cubed is definitely going to be smaller than 2 to the power of 5. Okay, because you're no longer multiplying by a decimal, but by something that is more than 1. Okay, so as you multiply, it gets bigger and bigger. So next, we can also look at reciprocal functions. So reciprocal functions are really, hold on. Did I miss a slide? Okay, so, oh, sorry, my fault. Not reciprocal function, the root function. So you can see that if your a, which is a constant here, right, is actually 1 over some n, which means that, for example, half. So if you have a to the power of half, then it is a root function. Okay, it is a root function. It is a power function, but the power is a fraction, right? Then you have a root function. So therefore, this happens when power is a fraction. Okay, then you get a root function. So therefore, I believe you know that x to the power of half is the square root, x to the power of 1/3 is the cube root, and so on and so forth. Okay, and you can observe that the root function, right, actually tries to flatten the curve, The simple reason is because you can see that, for example, square root. So let's say when you have y is equals to the square root of, let's say, for example, 1, you get 1. But when you have y equals to square root of 4, right, you're actually getting 2. So hence, what I'm trying to say here is that look at your input. If your input is 1, is here. But if your input is 4, so the bigger number that you give it, right, it tries to give you back a correspondingly not as big number. Okay, so 4 becomes 2, 9 becomes 3, and so on and so forth. So therefore, by this virtue, right, of the root, it flattens off the curve. Okay, so that is, of course, in contrast to when you have a power function, where you have the exponent, right, or the power not being a fraction, you have this, increasing trend, okay, as your x increases. So cube root. So then we come to the reciprocal function. So reciprocal function happens when the exponent is actually a negative term, right? So therefore, if you have -1, right, then you have this reciprocal function. And let me explain a little bit on the reciprocal function here. Now, following our discussion on the domain and range, actually, you know that f equals to 1 over x, right, is actually not being defined at x equals to 0, okay? Because 1 over 0 is undefined. So hence, we can observe that the domain of the function, right, does not include x equals to 0, okay? Hence, you have no line or no curve cutting through this y-axis here. Hence, you have no y-intercept, okay? Because the function is undefined at x equals to 0. Now, what is the behavior of the function? As x goes very close to 0, 1 over 0 becomes very big, okay? So we can see as x goes very close to 0, 1 over x will become very big. When you say become very big, right, it's actually going to plus minus infinity. Okay, plus infinity from this side, minus infinity from this side. So it goes to plus minus infinity. All right. Then we can also agree that as x goes to plus minus infinity, 1 over plus minus infinity, 1 over a super big number will go to 0. So hence, this accounts for their behavior at the ends here. Okay? So hence, you have this kind of shape, all right, coming from the analysis of 1 over x. Okay, here. So hence, you have what we call a vertical asymptote at x equals to 0 and a horizontal asymptote at y equals to 0. Okay, with the coordinate axis as the asymptotes. Asymptote is just a fanciful term, right? A fancy term for saying that as the graph, so-called, the graph tries to go toward that value, but never attains that value. So let me write down the definition here, right? Graph tends toward, but never touches. Okay, so that's what we call an asymptote. So you can see the example given here, which is known as Boyd's law. Boyd's law is related to this thing called the ideal gas law. I think some of you may have heard of this before when you learn chemistry or physics, right, in your secondary school. Okay, so it's actually related to the ideal gas law. So I think some of you may have heard of this expression, right, which is PV equals to RT, right? So when the temperature is constant, this is actually the ideal gas law. So therefore, when RT, where T is a constant, this temperature is a constant, right? You have this guy equals to C, okay? When T is a constant. So because R is the ideal gas constant, right? Which is also another constant. This R is a constant, okay? So PV equals to C, right? Really will look like this. Okay, the reason is because you can see that the volume, so if I rearrange this expression, right, you get V is equals to C over P. But C over P is just C multiplied by 1 over P. C is a constant, multiplied by 1 over P. Okay, so hence, right, if you plot V against P, you must get the reciprocal expression because it is 1 over P. Now, when you multiply by C, right, really, it just means that you take this value and multiply by a constant. So this 1 over P is the reciprocal. But then this C times 1 over P, right, we just take whatever value here and multiply by C. Okay, so after multiplying by C, it can look something like that. Okay, let me just try to draw more smoothly. So this is C over P. So this is 1 over P. Okay, of course, whether it goes up or down depend on what is the value of C, right? If it goes up, right, it really means that C is actually more than 1 here. Okay, so of course, if you have a decimal of 0.5 here, then you can expect this C over P to be lower than 1 over P. So Boyd's law actually makes use of the reciprocal function. Okay, and this actually makes sense if you think about it. When you go to a high altitude, right? Let's say you climb the mountain and you bring some potato chips with you, right? You know that at higher altitude, you're going to have lower pressure, but lower pressure causes the volume to increase. So hence your potato chip become very packed, okay, become very puffed, right, at high altitude because of the lower pressure. Correspondingly, at ground level or at sea level, right, you have higher pressure as compared to high up in the mountains, for example. Then you will have a smaller volume. Okay, you have a smaller volume. So this Boyd's law is in agreement with real life observations. Questions on power functions? Good. So let's move on. So just a recap, we have seen linear functions. All right, and then they are being used to model, for example, things like temperature changes. Okay, and then we also looked at the quadratic function, right, used to model a falling object, the height of a falling object. And then with this, we look at reciprocal function, which is being used to model things like how the volume changes according to pressure. Okay, according to pressure changes, assuming that the temperature is constant, right? So this is really trying to show you the different functions modeling real life phenomena. So next we move on to rational functions. So rational functions is actually pretty broad, actually pretty broad. So a rational function is actually a quotient of two polynomials. So I say pretty broad is because, right, this P and Q can be of any order. It can be of any order. Of course, in order for a rational function to be properly defined, the Qx here, right, cannot be zero, or else you got division by zero, you get undefined. All right. So for example, a reciprocal function is belonging to a class of the rational function when you have P of x being a constant, right, and the degree of order 0, and then Q of x is a linear function, a degree of a polynomial degree of order 1. Okay, so hence you have 1 over x, right, as the reciprocal function. And then you can observe that we can also have another example here whereby we have P of x is of degree 4. So this is degree 4 or order 4, order 4. And then this is order 2, order 2. Okay, so the net result is actually a rational function, right, of net order 2, because you always take the highest order. Okay, but however, you may wonder, why is this that the rational function, okay, how to find the range of the rational function in a while, Wei-Shen? So the domain of the rational function, right, will clearly depend on the quotient, or rather the Q of x here. Now, why is that so, right? Because you can see that for this quadratic function, there are actually two roots or two zeros. So we know that this x squared minus 4, this x squared minus 4 is actually factorized into x plus 4, or rather x plus 2, x minus 2. Okay, so x squared minus 4 you can factorize into x plus 2, x minus 2. So hence, right, what are the roots? Roots at x equals to plus minus 2. So which means that you have this x squared minus 4 returning you 0 when you have x equals to plus minus 2. So hence the asymptotes must happen there. Okay, asymptotes must happen there because asymptotes are points, right, whereby your function becomes undefined. Okay, undefined. So hence we have f of x do not exist or undefined at x equals to plus minus 2. Okay, hence resulting in the asymptotes. All right. So now, how do you find? So which means that besides this, right, you must agree that in this polynomial P, what is the domain? The domain is R. Okay, polynomials are defined everywhere, right? So hence, this guy, right, is also R except at plus minus 2. So this guy, the domain is also R given that x not equals to plus minus 2. Okay, so therefore you can see the domain of this rational function is actually R, but not including plus minus 2. Okay, because plus minus 2 you get do not exist or undefined, as you can inspect from here. Okay, so how do we get the range of the rational function? Now the range of the rational function, right, is not so easily defined. The reason is because you have to look at, you also have to look at the minimum and the maximum that the function can actually attain. Okay, let me see if there's a general approach for finding the range. Because it might not, there might not be a general approach. Because the polynomials can be of different degrees. I don't think there's a general approach. Okay, Wei Shen, my gut feel is I don't think there's a general approach to finding the range of a rational function, but I may be wrong. So let me check that up and reply you during the next lesson. Okay, but I don't think there's a general approach at this juncture, right? Because it really depends on what is the degree of P and what is the degree of Q here. Okay, and there are actually diagonal asymptotes as well. Okay, so if you look at this guy, right, actually there is a diagonal asymptote here, which means that there is an asymptote, right, whereby this function tries to tend to, but never touching this line. Okay, so it's not as straightforward as other elementary functions where you can look at the function and somewhat deduce the range just by looking at the function. Okay, so let me reply you again during the next lesson. So now we look at algebraic functions. So algebraic functions are even more general. The reason is because algebraic function, right, can be constructed by any sequence of algebraic operations, including addition, subtraction, multiplication, division, and taking roots. Okay, starting with polynomials. So you can see the square root of x squared plus 1 is the square root of a polynomial. So this is belonging to the class of algebraic functions. Okay, so the same thing goes for here. You can see that this is a polynomial divided by a linear function, but having a square root of a linear function here, right? So therefore, algebraic function you can just mix and match, all right? So it's actually very generic. So you can see further examples of algebraic functions here. So typically for algebraic functions, it's even more difficult to analyze, right? Because it's not so easy to see generally, right, what is the trend of the curve unless your algebraic function is very simple. Okay, so typically for complicated algebraic functions, right, we will need a graph plotter to assist us. So you can see here, they give us an example of an algebraic function that occurs in the theory of relativity. So this is really telling us that the mass of a particle traveling at the speed of v is given by its rest mass. Rest mass means that the particle is not traveling, okay, which means that the particle is not moving. So m naught, right, is actually the rest mass. Then divided by this square root of 1 minus v squared over c squared. So take note that this is a function of v. So which means that m naught and c, they are constants or they are parameters. Okay, so hence you can see that this is an algebraic function because it is taking the square root of 1 minus a reciprocal function. Oh, hold on. Oh no, this is not a reciprocal function. This is actually a quadratic function of v. Okay, so 1 minus a quadratic function, you take the square root and then you have the reciprocal of the entire thing. So hence this is just the class in the class of algebraic functions. And what this guy is really telling us is that the mass of a particle traveling at speed v, right, actually is constrained by the speed of light. Okay, so this is actually telling us nothing can travel faster than the speed of light. The reason is because as v approach c, so you get this 1 minus 1, right? So you get m equals to function of v, you get m naught over 1 minus 1. So this is actually undefined because you get m naught divided by 0. Okay, so which is this guy do not exist already. Okay, so this is do not exist. So this is telling us, right, that nothing can travel faster than the speed of light. So nothing travels faster than light. Okay, so I believe you have heard of that in so-called popular science. So we have a summary here, right? We have gone through polynomial functions, power functions, rational functions, algebraic functions, that we also seen certain real-life situations whereby these functions are used to model the behavior, okay, of some variables. Questions? before we move on to trigonometric functions. Actually, I aim to finish trigo functions today, but I don't think I can. So I'm just going to touch on trigo functions, and I think most students are kind of like scared or find it fuzzy with trigo functions, sine, cosine, tangent, secant, and so forth. Okay, but let me give you the big picture view of trigo functions. Now, trigo functions, right, actually just deal with projections. So this is the important concept that you must grasp. So trigo functions are functions that give vertical or horizontal projections. Okay. Now, why do I say that? The reason is because look at the quadrant. Okay, so I'm just going to draw like for example, the first quadrant. Okay, so projection of what? Projection of a hypotenuse of a rod, for example, of a a clock hand. So let's say I have this hypotenuse. So let's say this hypotenuse, right, is of length 1. Okay, that means the length is 1 meter, 1 cm, whatever, right? So let's say it's of unit 1. So what is the sign of the function? The sign of the function is actually the projection when you see it from the side onto the vertical axis. So this guy is actually giving you, right, sine theta. If let's say this angle is theta. Okay, so I repeat again, you have a hypotenuse of length 1, you project it on the vertical. So this vertical is actually giving you sine. Okay, the sine function, right? So hence, this is actually 1 times sine theta. This is 1. Okay, 1 times sine theta. So hence, sine function, a trigo function, right, is giving you the vertical projection. Correspondingly, the horizontal projection is on the x-axis, and this guy is actually giving you the cosine of the theta. Okay, so that's why I say trigo functions, they are just functions that give you the vertical as well as the horizontal projections, or if you like, y-axis as well as the x-axis projections of a hypotenuse. So why do I call this hypotenuse? I think you know that this sine, right, is actually here. This cosine is exactly here. So isn't this a triangle, a right angle triangle? So if this is a right angle triangle, right, this has to be a hypotenuse. This guy is known as the opposite, and this cosine theta part is known as the adjacent. Is that okay? So trigo functions, sine, cosine, are just vertical and horizontal projections. Okay? So let's look at further definitions here. Now, sine theta is given by opposite over hypotenuse. Opposite over hypotenuse, right? I believe now you know why already. It's because you are actually projecting this hypotenuse. So therefore, let's say this is not 1. Okay, it can be any length, it may not be 1. So let's say I call this hypotenuse h of length h. So what's going to happen is that this now becomes h sine theta, right? Because just now it's of length 1, right? So become 1 times sine theta. But now it's of length h. So now become h sine theta because it's of length h, right? So hence, this guy, right, is actually h cosine theta now. H cosine theta. Okay? So therefore, now we have the condition, which is opposite is actually equivalent to h projected by the sine theta. Okay, that's why I say opposite is the projection of h on the vertical. So hence, rearranging, you get sine theta is equals to opposite over hypotenuse. All right, so whenever you see sine, that means, right, it is opposite to the angle. I repeat again, the angle here, theta, on the opposite side to the angle, you always have sine. On the side that is adjacent to the angle, adjacent means what? Adjacent means beside. You always have cosine. Okay? So let me test you. If I have another angle phi here, so can you tell me what is this O? Or maybe let's not call this opposite. Let's call this L. Let's call this length L here. O equals to L. So can you tell me what is the length of L? Expressed in terms of phi. Maybe let's call this phi and not theta. Any guesses from you? Anyone? L must be equals to what? L is opposite, but this is with respect to theta. I want an expression that is with respect to phi. Can anyone give me the expression? No? Check. This L, right? This side. Is it opposite or adjacent with respect to phi, to the angle phi? Is it opposite or adjacent? This L. Is it opposite or adjacent to the angle phi? Very good, adjacent. So which means, right, L must be equivalent to H adjacent to phi. So therefore, this guy must be H cosine phi. Okay? So therefore, L equals to H sine theta is also the same as L equals to H cosine phi. Okay, because they are actually angles in the triangle, right? And you can press your calculator for that. And let me just show you. So let's say, give you an example. Now you have, okay, this is right angle. Let's make it right angle. So let's say this guy, right, is actually 30 degrees. Then this guy got to be what? 60 degrees. So let's say, for example, if I want this length, so this length, let's give this maybe 2. So what is this length? 2 sine 30 degrees, right? So what is 2 sine 30 degrees? You can press your calculator. Equals to 2 times sine 30 degrees. So it's 1, right? It's 1. So let us go back. So this guy is actually equivalent to 1. But what about with respect to the 60 degree here? Now this guy is also 2 cosine 60 degree. So you check, what is 2 cosine 60 degree? Equals to 2 times cosine 60 degree. Oops. So isn't this 1? So sine 30 is equivalent to cosine 60. Okay, we'll come to those expressions later on. But you know that by this example, right, you know the relationship between sine and cosine now. Okay, so sine of the angle is always opposite to the angle. That's why, right? Can imagine this is like sine, like C, okay? Like the angle is looking at it, right? So therefore, cosine is always the adjacent. So coming back to our relationships here, I hope this becomes clear already. Sine always opposite, right, over hypotenuse. Cosine always adjacent over hypotenuse. So it's like you take with respect to the hypotenuse and you try to look at the projections on the opposite of the angle as well as the adjacent of the angle. And the rest of the angles, the rest of the functions are all derived from sine and cosine. Okay? Tangent is cosine over sine. Oh, sorry, my fault. Sine over cosine. So you know that this is opposite over hypotenuse divided by adjacent over hypotenuse. So the hypotenuse cancels off, divide off. So you get opposite over adjacent. So that's tangent. Okay, so tangent is equals to sine over cosine. Cosecant is 1 over sine. So 1 over sine, of course, just reciprocal. Okay, switch the fraction or inverse the fraction. Secant is 1 over cosine. Then cotangent is just 1 over tangent. So it's all derived from sine and cosine, which are simply projections. Okay, so that's the big and the broad picture, right, of trigonometry is projections. So hence, I actually want to show you this nice Wikipedia GIF here, and then we'll just maybe end the class today. Look at this, right? Sine. Look at this red line. Isn't this tracing the height here? The vertical height, right? So it's a vertical projection. Look at this cosine. Isn't this tracing the length in the x-axis, the horizontal length, right? So therefore, sine and cosine functions, right? You have sinusoidal function like a waveform, okay? And because your hypotenuse or your clock hand is rotating around a circle, the projection lengths are changing correspondingly. Okay? So with that, I think I would like to call it a day. Let me see. Okay, I'll just leave the rest for the next Wednesday lesson. Questions? A lot to process. I agree. But the initial part is quite tight because they try to squeeze all the revision. Because this part is still under revision, you have not touched calculus yet. So therefore, we try to squeeze all the basics or the prerequisites of calculus, right? Or pre-calculus, they call it, okay, within 1 week. So it's okay if we exceed a little bit. Okay, by the way, your homework submission is next Friday. So therefore, if you look at your homework one, you can actually do most of it already. Oops. You can actually do most of it already. But however, I think some questions you can't do yet. So therefore, the remaining questions, if you can't do, you can wait till we go through the rest next Wednesday. Okay, so you can see question 2. I think this is a linear function you can do already. Let me see. Oh, actually, you can do all because trigo functions are not covered in homework 1. So you can do the whole homework 1 already. Yeah, a lot to process because they try to squeeze the revision within 1 week. So it's okay if we, extend to the next week a little bit. Okay, so please ask me question in Teams because I don't get any questions, right? It's all, just me posing stuff and talking to myself. Okay, so please ask me questions. If you are shy, if you are the mysterious and secretive type, you don't have to, type it here, right? You can chat, you can private chat with me, right? So if you want to share your questions and maybe discuss with your friends as well, then feel free to type, okay, your question or your comments here. All right. So with that, I am going to call it a day. So thank you for your attention and you guys have a good lunch.